fading of light when galaxies drift apart.
Have you ever looked up at the night sky, filled with countless stars, and felt a sense of wonder? Each of those tiny lights is a star, many of them in our own Milky Way galaxy. But what about the other galaxies? Those vast islands of stars, gas, and dust, separated by unimaginable distances. For centuries, we thought the universe was a grand, static stage. But we were wrong. The universe is expanding, and it's expanding at an accelerating rate. This cosmic expansion is leading us toward a future that is both fascinating and profoundly lonely. A future where the light from other galaxies will, one by one, fade away. Imagine you're on a ship in the middle of a vast ocean at night. All around you, you see the lights of other ships. Now, imagine all those ships start sailing away from you, faster and faster. At first, you can still see their lights, but they get dimmer. Eventually, they move so fast that their light can no longer reach you. They disappear over the horizon, and you're left alone in the darkness. This is, in a cosmic sense, what's happening to our universe. To understand this, we need to go back about a century to the work of two incredible astronomers, Vesto Slipher and Edwin Hubble. Slipher was the first to notice something strange. When he looked at the light from distant galaxies, he saw that it was almost always shifted toward the red end of the spectrum. This is called redshift. Think of it like the Doppler effect for sound. When an ambulance siren is moving away from you, its pitch drops. With light, when an object is moving away from us, its light waves get stretched out, shifting them toward the red, lower energy end of the spectrum. Slipher's observations showed that most galaxies were rushing away from us. Then came Edwin Hubble. Using the powerful Hooker telescope at Mount Wilson Observatory, he made a groundbreaking discovery. Not only were these galaxies moving away from us, but the farther away a galaxy was, the faster it was receding. This became known as Hubble's law. This was the first concrete evidence that the universe itself was expanding. It wasn't that galaxies were flying through a static space like shrapnel from an explosion. Instead, the very fabric of space-time itself was stretching, carrying the galaxies along with it. You can visualize this with a simple balloon. Draw some dots on the surface of an uninflated balloon. Each dot represents a galaxy. Now, as you blow up the balloon, what happens? Every dot moves away from every other dot. From the perspective of any single dot, it looks like all the others are rushing away. The farther apart the dots are, the faster they appear to separate because there's more expanding space balloon surface between them. This is exactly what's happening in our universe. Our Milky Way isn't a special center. An observer in any other galaxy would see the same thing, all other galaxies rushing away from them. For a long time, astronomers debated the ultimate fate of the universe. Would gravity eventually win, pulling everything back together in a big crunch, or would the expansion continue forever? The answer came in 1998. And it was a shocker. Two independent teams of astronomers studying distant supernovae stars that act as cosmic lighthouses found that the expansion was not slowing down. It was accelerating. Something was pushing the universe apart, counteracting the pull of gravity. This mysterious force was given a name: dark energy. We still don't know what it is, but we know it's there. It seems to be a property of space itself, and it makes up about 70% of the entire energy density of the universe. As space expands, more space is created, and with it, more dark energy, which in turn causes space to expand even faster. It's a runaway process. So, what does this accelerating expansion mean for our view of the cosmos? It means that galaxies are being pushed away from us at incredible speeds. 4 galaxies that are already very far away. The space between us and them is expanding so fast that their recession speed exceeds the speed of light. Now, you might think, wait, I thought nothing can travel faster than light. And you're right, nothing can travel through space faster than light. But this is different. It's space itself that's expanding. There's no cosmic speed limit for the expansion of spacetime. As these galaxies cross this cosmic event horizon, the light they emit can no longer reach us. It's like trying to swim upstream against a current that's faster than you can swim. No matter how hard you paddle, you're carried backward. The light from these galaxies is forever trapped, unable to bridge the ever-widening gulf of space between us. This process has already begun. The most distant galaxies we can currently observe are already beyond our reach. The light we see from them tonight was emitted billions of years ago. Since then, they have been carried away by cosmic expansion to a point where any light they emit, today, will never, ever get to us. We are, in effect, watching their ghosts. As time goes on, more and more galaxies will cross this cosmic event horizon. Over billions and even trillions of years, the night sky will begin to change. First, the most distant galaxies will disappear from view. Then, the closer ones will follow. One by one, the islands of stars will blink out of our sight. The universe, once teeming with countless galaxies, will appear to empty out. Eventually, our local group, a small cluster of galaxies, including the Milky Way and Andromeda, which are gravitationally bound together, will be the only thing left. Andromeda is actually on a collision course with us, and in about 4.5 billion years, our two galaxies will merge to form one giant elliptical galaxy, which some have nicknamed Milkomeda. This new, massive galaxy will be our entire visible universe. Every other galaxy will have receded beyond the cosmic horizon, their lights stretched into oblivion, leaving our galactic home an isolated island in an endless, dark void. Future astronomers in this far-flung era will look out into the cosmos and see ... nothing. Just the stars of their own galaxy. They would have no way of knowing that other galaxies ever existed. The clues to the Big Bang, the cosmic microwave background radiation, will have been stretched to wavelengths so long they'll be undetectable. To them, the universe might appear static, eternal, and solitary, exactly what we thought before Hubble's revolutionary discovery. They would be living in a cosmic echo chamber, unaware of the true, grand scale of reality. It's a humbling and somewhat melancholic thought. We are living in a very special time in the universe's history, a cosmic golden age where we can actually see the grand tapestry of the cosmos, observe the evidence of its explosive birth, and witness the vast community of galaxies. We are privileged to be the generation that can piece together this incredible story. The fading of the light is a slow, inexorable process, happening on timescales almost too vast for us to comprehend. But it serves as a powerful reminder of how dynamic and ever-changing the universe truly is. The sky we see tonight is a fleeting spectacle, a temporary window into the grandeur of the cosmos that will not last forever. So the next time you look up at the stars, take a moment to appreciate it. You're not just seeing lights in the sky, you're seeing a snapshot of a universe in motion, a grand cosmic ballet that we are incredibly fortunate to witness. Have you ever stared into the night sky and wondered what lies in the deepest, darkest corners of the cosmos? Out there, in the silent void, lurk the universe's most enigmatic and powerful monsters, black holes. These are not just empty spaces, they are cosmic behemoths, regions of space-time where gravity is so intense that nothing, not even light, can escape their grasp. Imagine a celestial giant, a gravitational titan, ruling over its domain with an unyielding grip. Today, we're going on a journey to the edge of reality, to explore the reign of these incredible cosmic phenomena. What are they? How do they form? And what happens if you get too close? Buckle up, because we're about to dive headfirst into the abyss. So, what exactly is a black hole? The concept might sound like science fiction, but it's a very real prediction of Einstein's theory of general relativity. Picture this. You take an immense amount of mass and squeeze it into an incredibly tiny space. The gravitational pull of this object becomes so powerful that it warps the fabric of space-time around it, creating a deep, inescapable well. This well is the black hole. At its heart lies a singularity, a point of infinite density, where our current laws of physics simply break down. It is a place where all the mass of a collapsed star is crushed into a space smaller than a single atom. Surrounding this singularity is the event horizon, often called the point of no return. Once you cross this invisible boundary, there's no turning back. Your fate is sealed, and you're pulled inexorably toward the center. It's a one-way trip to the ultimate unknown. Black holes aren't all created equal. They come in different sizes, each with its own fascinating origin story. The most common type are stellar mass black holes. These are the final, dramatic act in the life of a massive star, one that's at least 20 times more massive than our own sun. When such a star runs out of fuel, it can no longer support its own colossal weight. Its core collapses under the force of its own gravity in a fraction of a second, triggering a spectacular explosion known as a supernova. While the outer layers of the star are blasted out into space, the core continues to collapse in on itself, crushing down until it becomes a stellar mass black hole, typically a few times the mass of our sun. Think of it as the ghost of a giant star, left behind to haunt the cosmos. But then, there are the true giants, the undisputed kings of the universe, supermassive black holes. These behemoths are millions, or even billions, of times more massive than our sun. We find them lurking at the heart of nearly every large galaxy, including our own Milky Way. At the center of our galaxy, about 26,000 light-years away, lies Sagittarius A*, a supermassive black hole with a mass equivalent to about 4 million suns. How these giants grow so massive is still one of the biggest mysteries in astrophysics. Do they start small and grow by gobbling up stars and gas over billions of years? Or did they form from the direct collapse of massive gas clouds in the early universe? Scientists are working tirelessly to piece together the puzzle of these cosmic rulers. So, what's it like to encounter one of these cosmic titans? The gravitational effects of a black hole are truly mind-bending. As you get closer, the force of gravity becomes exponentially stronger. This leads to a bizarre and terrifying process known as spaghettification. Imagine you're falling feet first toward a black hole. The gravitational pull on your feet would be so much stronger than the pull on your head that your body would be stretched, like a piece of spaghetti, until you're torn apart at the atomic level. It's not a pleasant thought, but it's a stark illustration of the raw power we're dealing with. It's this immense gravity that allows black holes to consume everything that ventures too close, from stray asteroids to entire stars. We've seen evidence of stars being ripped apart in what are called tidal disruption events, a cosmic feeding frenzy that releases a brilliant flash of light, detecting something that, by definition, emits no light. Sounds impossible, right? But astronomers are incredibly clever. We can't see black holes directly, but we can see their effects on the space and matter around them. One way is by observing the orbits of stars. At the center of our galaxy, we can track stars whipping around an invisible point at incredible speeds. The only thing that could exert enough gravitational force to make them move like that is a supermassive black hole. Another key method is to look for accretion disks. As gas and dust are pulled toward a black hole, they form a swirling, superheated disk around it. The friction within this disk heats the material to millions of degrees, causing it to glow brightly in X-rays and other wavelengths. Telescopes like the Chandra X-ray Observatory are our eyes, allowing us to see these telltale signatures of a black hole's meal. And then, in 2019, humanity achieved the impossible. The Event Horizon Telescope, a global network of radio telescopes working in unison, captured the very first direct image of a black hole. It wasn't a picture of the black hole itself, but of its shadow cast against the bright, glowing accretion disk surrounding it. The image of the supermassive black hole at the center of the M87 galaxy was a stunning confirmation of Einstein's theories. We could finally see the point of no return with our own eyes. It was a monumental achievement, a testament to human ingenuity and our relentless quest to understand the universe. This image transformed black holes from a theoretical concept into a tangible, observable reality. Beyond just being cosmic destroyers, black holes play a crucial role in the evolution of the universe. The immense energy and radiation blasting out from the accretion disks of supermassive black holes influence the entire galaxy they inhabit. This feedback can regulate star formation, either by blowing away the gas needed to form new stars or by compressing it to trigger bursts of starbirth. They are the great architects and regulators of the cosmos. Black holes are also responsible for creating some of the most powerful events in the universe. The merging of two black holes. When two black holes spiral into each other and merge, they release an incredible amount of energy in the form of gravitational waves. ripples in the fabric of space-time itself. These waves, first detected in 2015 by the LEGO experiment, have opened a brand new window to the universe, allowing us to hear the cosmos in a way we never could before. The study of black holes pushes the boundaries of our knowledge, forcing us to confront the limits of physics. What happens inside a black hole? At the singularity. Does information that falls in truly get destroyed forever, violating the fundamental principles of quantum mechanics? This is known as the black hole information paradox, a deep puzzle that physicists like Stephen Hawking dedicated their lives to. These questions lead us to even more exotic ideas, like the possibility of wormholes, theoretical tunnels through spacetime that could connect distant points in the universe, or perhaps even connect to other universes entirely. While purely speculative for now, these ideas show how black holes are not just objects to study, but gateways to understanding the fundamental nature of reality itself. From the ghosts of dead stars to the colossal engines at the hearts of galaxies, black holes are an integral, awe-inspiring part of our universe. They are not just objects of destruction, but also agents of creation and change, shaping the cosmos on the grandest of scales. They challenge our understanding of space, time, and gravity, and with every new discovery, they reveal a universe that is far stranger and more wonderful than we could ever have imagined. The reign of black holes is a testament to the power and mystery that still awaits us in the dark. Ever looked up at the night sky and wondered where it all ends? Not just the stars and galaxies, but time itself. What happens when the last star flickers out and the universe falls silent? Today, we're journeying into the furthest reaches of the future to explore one of the most profound and mind-bending concepts in cosmology: the heat death of the universe. Don't worry, it's not as grim as it sounds. It's a story of energy, entropy, and the ultimate fate of everything. So, what exactly is this heat death? To understand it, we need to talk about something called entropy. You can think of entropy as a measure of disorder or randomness. Imagine you have a hot cup of coffee. The heat energy is concentrated in the cup. If you leave it on the table, it will gradually cool down, releasing its heat into the room until the coffee and the room are the same temperature. The energy hasn't disappeared, it's just spread out. The universe works in a similar way, but on an unimaginable scale. This is all based on the second law of thermodynamics, a fundamental rule of our universe. It states that in an isolated system, entropy always tends to increase. In simpler terms, things naturally go from a state of order to disorder. An egg can scramble, but you can't unscramble it. A drop of ink spreads out in water, but it won't gather itself back into a drop. The universe is the ultimate, isolated system. From the incredibly hot, dense, and orderly state of the Big Bang, it has been expanding and cooling ever since. Its energy is constantly spreading out, and its entropy is constantly increasing. The heat and heat death doesn't mean the universe will become scorching hot. It's actually the opposite. It refers to thermal energy. Death refers to the end of all thermodynamic free energy, the energy available to do useful work, like forming stars, powering life, or even just thinking a thought. When the universe reaches a state of maximum entropy, all the energy will be perfectly, uniformly distributed. There will be no hot spots and no cold spots. No energy gradients means no work can be done. It's a state of perfect equilibrium. Let's fast forward our cosmic clock to see how this unfolds. The journey to heat death is a long one, playing out over timescales that make the current age of the universe seem like a fleeting moment. First, in about 100 trillion years, the era of stars will come to an end. All the available hydrogen gas will have been used up to form stars, and those stars will have lived out their lives. The last red dwarfs, the longest living stars, will finally burn out, plunging the cosmos into a profound darkness. The universe will be populated only by the remnants of stars, white dwarfs, neutron stars, and black holes. The age of starlight will be over. But the story doesn't end there. We enter what's called a degenerate era. Over even more astronomical timescale sync, trillions upon trillions of years, these stellar remnants will slowly decay. According to some theories, even protons themselves, the building blocks of matter, might eventually decay. If this is true, then everything we consider matter will slowly dissolve into a sea of lighter particles like photons and electrons. The universe will become an incredibly dilute, cold soup of particles. The only things left holding their form will be the most stable objects of all. Black holes. Now we enter the black hole era for a period of time so vast it defies description. We re-talking up to 10 to the power of 100 years, a number known as Aguga black holes, will be the last major players on the cosmic stage. They will be the only organized structures left, silently drifting through the empty, expanding void. But even they are not eternal. Thanks to a phenomenon predicted by Stephen Hawking, called Hawking radiation, black holes very, very slowly evaporate. They leak tiny amounts of radiation back into space, losing mass over immense periods. The smallest black holes will evaporate first, followed by the larger ones, until even the supermassive black holes at the centers of what were once galaxies finally fizzle out in a final, weak flash of light. And with the evaporation of the last black hole, we arrive at T-dark era, the final stage of the universe before heat death. What's left? A vast, cold, and almost perfectly empty void, filled with a sparse, uniform mist of photons, neutrinos, and other fundamental particles. All matter has decayed. All black holes have evaporated. The energy of the universe is now spread so thinly that the temperature is just a sliver above absolute zero. There are no structures, no complexity, no temperature differences. This is the state of maximum entropy. No more change is possible. No more events can happen. Time, as we understand it, a sequence of cause and effect, of one thing happening after another, loses its meaning. The arrow of time dissolves. This is the heat death of the universe, a state of eternal, unchanging stillness. It's a strange and sobering thought, isn't it? The end of everything. But here's the beautiful part. This future is so incomprehensibly far away that it's purely theoretical. We are living in the universe's vibrant, energetic youth. We are here in the stelliferous, the age of stars. The cosmos is filled with light, energy, and boundless potential. We are part of a grand cosmic story that is still being written. The fact that we, as a species, can even contemplate the end of the universe is a testament to the incredible complexity and wonder that has emerged from that initial ordered state of the Big Bang. So, instead of seeing it as a grim ending, we can see the theory of heat death as a reminder of just how precious and extraordinary this moment is. The universe is alive with activity, and we have the privilege of witnessing it. We are part of a fleeting but brilliant cosmic dawn. Let's make the most of it, continue to explore, to question, and to marvel at the sheer scale and beauty of it all. How does it all end? It's a question that has captivated humanity for millennia. We know how it all began, with the Big Bang. But the ultimate fate of our universe is still one of the biggest mysteries in cosmology. Today we're diving into 3 of the most mind-bending theories. The Big Rip, the Big Crunch, and the Big Bounce. Which one will it be? Let's find out. First, let's set the stage. The fate of the universe is a cosmic tug-of-war. On one side, you have gravity, constantly trying to pull everything back together. On the other side, you have dark energy, an enigmatic force that's pushing everything apart, causing the universe to expand at an accelerating rate. The winner of this epic battle determines our ultimate destiny. Let's start with the most dramatic scenario, the Big Rip. Imagine dark energy is overwhelmingly powerful, like a cosmic bully that just won't quit. In this model, the expansion of the universe doesn't just continue. It gets faster and faster, exponentially. At first, the effects are subtle. Distant galaxy clusters would be pulled apart. Then, galaxies, like our own Milky Way, would be torn asunder. The gravitational bonds holding stars and planets together would fail. Solar systems would disintegrate. But it doesn't stop there. As the expansion becomes infinitely fast, the very fabric of space-time is eventually, the forces holding atoms together would be overcome. Planets, stars, and even you and I would be ripped apart into our fundamental particles. And finally, in the last fleeting moments, those particles themselves would be torn into nothingness. It's a violent, spectacular end, where the universe literally rips itself to shreds. Chilling, right? Now, let's consider the opposite. What if gravity wins the tug-of-war? This leads us to the Big Crunch. In this scenario, the pull of gravity eventually overcomes the push of dark energy. The universe's expansion would slow down, halt, and then reverse. Everything would start moving back towards everything else. Galaxies that are currently rushing away from us would change direction and head straight for us. The universe would get hotter and denser as it contracted. Imagine the Big Bang playing in reverse. Galaxies would merge, stars would collide, and the cosmos would become a chaotic, fiery furnace. Eventually, all matter and energy would collapse back into an infinitesimally small, hot, dense point, similar to the singularity from which the universe began. It's a cosmic reset button, a grand implosion bringing everything back to a single point. A neat, tidy, but incredibly fiery end. But what if the end is also a beginning? That's the idea behind our third theory, the Big Bounce. This model takes the Big Crunch and adds a fascinating twist. Instead of collapsing into a final singularity, some theories suggest that as the universe contracts, it could bounce at the point of maximum compression. New physics, perhaps, from quantum-gravity could repelling everything and triggering a new Big Bang. In this cyclical model, our universe could be just one in an eternal series of universes, each one born from the ashes of the last. A big crunch leads to a big bounce, which leads to a new expansion. A new universe with its own stars and galaxies, which eventually collapses again. It's an endless cycle of cosmic death and rebirth. We might be living in just one chapter of an infinite cosmic story. So, which will it be? A violent rip, a fiery crunch, or an eternal bounce? The answer hinges on the true nature of dark energy, something scientists are working tirelessly to understand. Current observations suggest our universe's expansion is accelerating, which might favor the Big Rip, but we're still far from a definitive answer. The cosmos keeps its secrets well. What do you think is the most likely fate of our universe? Let me know your thoughts in the comments below. It's a mind-boggling topic, and it reminds us of the incredible scale and mystery of the cosmos we are a tiny part of. We know about the Big Bang, that explosive start to everything we know. But what about the end? And more importantly, could the universe begin again? It's a question that has puzzled scientists and philosophers for centuries. And today, we're diving deep into the theories that try to answer it. First, let's talk about the potential endings. The fate of our universe hinges on a cosmic tug-of-war between the momentum of expansion from the Big Bang and the gravitational pull of all the matter and energy within it. One popular theory is the Big Freeze, or heat death. In this scenario, the universe just keeps expanding forever. Stars burn out, galaxies drift apart, and eventually, everything cools down to a near absolute zero. It's a cold, dark, and lonely end where all activity ceases. The universe would become a vast, silent expanse of dead stars and black holes. Then there's the Big Rip. This one is a bit more dramatic. It's driven by something called dark energy, a mysterious force that's accelerating the expansion of the universe. If dark energy gets stronger over time, the expansion could become so violent that it literally tears everything apart. First, galaxies would be ripped from their clusters, then stars from their galaxies. Eventually, planets, and even the atoms that make up our bodies, would be shredded into their fundamental particles. It's a very definitive and very messy conclusion. But what if gravity wins the tug-of-war? That brings us to the Big Crunch. In this scenario, the gravitational pull of all the matter in the universe is strong enough to halt the expansion and reverse it. The universe would begin to contract, with galaxies rushing back towards each other. Everything would get hotter and denser, culminating in a spectacular implosion, a sort of Big Bang in reverse. All of space and time would collapse into an infinitely hot, infinitely dense singularity, just like the one that started it all. This is where things get really exciting. The Big Crunch opens the door to the idea of a cyclical universe. What if that final singularity isn't the end, but a new beginning? This concept is known as the Big Bounce. Imagine the Big Crunch leading directly to another Big Bang. The universe would be like a cosmic accordion, expanding and contracting, being born, dying. and being reborn in an endless cycle. Each universe might even have slightly different physical laws, creating an infinite variety of cosmic possibilities. Over eons, modern physics, especially string theory and loop quantum gravity, have given new life to these cyclical models. They suggest that as the universe collapses, quantum effects could kick in, preventing a true singularity and instead bouncing the universe back into a new phase of expansion. Think of it like a cosmic reset button. It's a beautiful, elegant idea that the end of one universe is simply the seed for the next. It implies that creation isn't a one-time event, but a continuous, eternal process. So, could the universe begin again? We don't have a definitive answer yet. Our understanding of dark energy and the ultimate laws of physics is still incomplete. Whether our destiny is a cold freeze, a violent rip, or a fiery rebirth remains one of the greatest mysteries. But exploring these possibilities stretches our imagination and deepens our connection to the cosmos. The universe is a story still being written, and we are lucky enough to be here to read a few of its pages. Thanks for joining me on this cosmic journey today. What do you think is the ultimate fate of our universe? Let me know in the comments below. And if you enjoyed this exploration of the cosmos, don't forget to like this video and subscribe for more deep dives into the mysteries of science. See you in the next one.